Hi, my name is Jorge Figueras and I will be presenting Capstone1 Phase B Functional Finger Prosthetic Design Subsystem Control. In the outline, we have subsystem trait studies, subsystem architecture into components, trait studies for critical components, subsystem risk assessment, and project planning. Subsystem trait studies. How the control subsystem will work. Option 1. Electrical prosthesis. This prosthesis uses as a source of energy electric implements such as electric motors in the terminal device, wrist, or elbow with a rechargeable battery. Electrical prostheses are controlled in a number of ways, either with a servo control, push button control, or harness switch button. On certain occasions, these forms are combined for their best functionality. A socket is used, which is an intermediate device between the prosthesis and the stump, achieving its suspension by suction. Its acquisition and repair are expensive, with other obvious disadvantages, such as being careful when exposed to a humid environment and the weight of the prosthesis. Here we have a diagram of our electrical prosthesis. Option 2. Pneumatic prosthesis. Pneumatic prostheses are devices that use compressed air as a source of energy to produce the movement of the prosthesis. Pneumatic muscle actuators. Their main advantage is greater speed and greater strength. As a disadvantage is high maintenance cost and the complexity of its accessory device stand out. Here we have a diagram of our pneumatic prosthesis. In the option 3, we have myoelectrical prosthesis. These are electronic prostheses controlled means of an external bioelectrical power. Today, they are the type of artificial limb with the highest degree of rehabilitation, since they synthesize the best aesthetic appearance, have great grip strength and speed, as well as many possibilities for combination and enlargement. Myoelectrical control is probably the most popular control scheme. It is based on the concept that wherever a muscle in the body contracts or flexes, it produces a small electrical signal that created by chemical interaction in the body. This signal is very small, and it captured with surface electrodes that enter in contact with the surface of the skin. This type of prosthesis has the advantage that it only requires the user to flex their muscles to operate. Unlike body-operated prostheses, they require that general movement. Plus, it removes the suspension harness. The disadvantage is that they use battery systems that require maintenance to recharge and discharge, and that it must be discarded and replaced eventually. They also have a high cost and a high weight. Myoelectrical prostheses are those that have greater applications in today's world due to their easy use, their greater aesthetic degree for the person who uses them, and the greater force they perform, and the greater speed and with high precision. Here we have a diagram of our myoelectrical prosthesis with the sensors inside. We continue with the subsystem trait studies with the rating weighting. Our problem statement is to choose a system that best meets the requirements of the client. As you can see, this our criteria. The option 3, myoelectrical prosthesis, is the best who meets the requirements of our client. Subsystem architecture into components. Control system is divided into motor, processor, and sensors. The motor function is to make the force to move the fingers. The processor sends the signal of the sensor to activate the motor, and the sensor receives the electrical signal made by the user. Here we have the interface diagram. A one-hand prosthesis that can lift a weight of less than 5 pounds is modified with a myoelectrical system and a motor so that if a person is using the one-hand prosthesis, assuming that he knows to use it and assuming that the prosthesis has full charge and with all components in perfect condition, want to grab and lift a 5-pound object, they can do it quickly, safely, and efficiently. For this, we have to know the following data. Force does the finger of one hand have to do to grab a 5-pound object? How much force does the user have to do to send the signal to the myoelectrical sensor? How long does it take for the myoelectrical sensor to capture it and send the signal to the processor? How long it takes for the processor to send the signal to the motor to start? How long does it take for the motor to run the finger to be completely closed? How long does it take to turn off the engine for the finger to reopen? Here we have a diagram of the muscle sensor connected to the processor that is connected to the motor that is connected to the finger, with the finger trajectory open and closed. Here we have the traits studied for the critical components. The motor. We have these three motors: brushless DC motor, linear actuators, and stepper motors. As you can see, the brushless DC motor is the best, has met the requirements of the client. We have the processors. As you can see, we have Arduino Mini, Arduino Micro, and Arduino Nano. The best that meets the requirements of the client is the Arduino Micro. Here we have the sensors. We have gravity analog sensor by O-motion and myaware muscle sensor. The best sensor is the myaware muscle sensor. Here we have the subsystem risk assessment. The risks are wires or disordered disconnection, and the mitigation strategy for that is to prepare the solder equipment, soldering iron, tin, heat, shrinks, tubing, and protect the solder by sliding sheath. Risk B is battery discharge quickly. The mitigation for that is to use a lithium rechargeable battery or replace the batteries. Risk C. Motor is not receiving enough current. As mitigation strategy, we have high performance and efficiently BLDCs, that is the motor, are broadly and more efficiently than their brushless counterparts. They use electronic capabilities, allowing for fast and precise control of the speed and position of the motor, and must have adjustable DC/DC power converter. Risk D. Motor is making noises. The mitigation strategy is that motor will be brushless DC motors, that is low noise. Motors operate more quietly because they don't have brushless that constantly make contact with other components. E is sensor do not receive enough signal. As a mitigation strategy, we have the sensor will be myaware muscular sensors. Risk F, sensor do not attach correctly to the surface. Sensor can have a gel electrode and AGCL for best receiving signals and best attachment. And the risk G, we have circuit receiving error signals. As a mitigation strategy for that, we have to build a cover for the circuit for the signal interferences. In the right, we have the risk assessment matrix with each risk categorized. Project planning. We are planning to present phase C1 in December 1 of this year. Thank you.